leader Li Weifan from Team Wu Yikanhua, and here I would like to introduce my team members, Xu Kaiyi, Li Qingyue, Liu Yuhui, and Wilson. Thank you.
Non-writer or all-nighter?
Hi, we are non-riders from Taipei American School, and I'm the captain, Darren Z. Here we have Billy, Ethan Ho, Ethan Hu, and Kenneth.
Okay.
Thank you.
Honorable jury and fellow competitors and the team members of Team Korea, and we're from Jiachen Senior High School. This is Guo Yuan, Sharon Ba, Hou Jun, and Yu Shui Yang, and I'm the team leader of the company.
Okay, so now let's begin with the challenge stage. So the opponent team should challenge.
Okay, so we challenged the reporter to magnetic mechanic oscillator.
Which is number
Six.
number 6. Okay, problem number 6.
So this is the reporter from the reporter team, and our team accepts the challenge.
Okay, problem accepted. So problem number 6, and you have 5 minutes for preparation, right? Yeah. So write down the name of your presenter.
Honorable judges, worthy opponents, this is the reporter from Tanhua team. And today I will be reporting problem number 6, which is magnetic mechanical oscillator. So here I would like to reiterate the problem again, which is to secure the lower ends of 2 identical leaf springs to a magnetic base and attach magnets to the upper end such that they repel and are free to move, as demonstrated in the gym. So, and then investigate how the movement of the springs depends on relevant parameters. And for this experiment, our team decided to focus on first explaining this phenomenon, second establishing a model and the theory, third investigating the relevant parametric relations. So before all of the discussions, I would like to first introduce the experiment set up by our team. So according to the problem statement, we prepared leaf spring and magnets. And in order to fix the leaf spring, we used micrometer to fix it. Then we used high-speed camera and then fixed on the tripod, and then used some of the softwares listed above to track and analyze the motion of the magnets. So now I will be starting to introduce the theory and model that came up by our team. So first I'll be explaining the oscillation of single leaf spring on its own. And using the force analysis, which is shown here, we can then come up with a recovery torque for one of the leaf spring. And here we utilize small angle approximation as shown here, since when angle is small, theta can be approximated to be the same as sine theta. And then we can obtain the differential equation above, which is the equation for angular velocity, which is sigma L over I and then square root. So so by solving the differential equation, we can then derive the angular velocity. So after obtaining the equation, we can then compare the theory to the experimental results. Theoretical value of when the length is 9 centimeters is 0.08658, and then after our experiment, we can deduce that when the length is equal to 9 centimeters, the period is 0.0906 seconds. And then we can focus on when the length is 11 centimeters. So when the theoretical value for the period when the length is 11 centimeters is 0.1453 seconds, and the experiment result shows that when the length is equal to 11 centimeters, the period is 0.152 seconds. So next, our team had started to consider the torque exerted on the leaf spring by the magnetic force, where K in this shown on the slides is a function used to calculate the arm of the magnetic torque. And in our experiment, K is a function that is related to theta. However, this function may vary because of different leaf springs used. In our experiment, K, after some evaluation, K can be evaluated through a linear equation with a linear relationship to the theta. So taking magnetic force torque into consideration, the new equation for the angular velocity and period can then be derived. So after deriving the new equation, we can then again compare the theoretical value and the experimental results. With the initial condition listed here, theoretical value of the period would then be 0.151 seconds, and the experimental value is 0.164 seconds. So all the discussions above was focused on the condition when one of the leaf is static. And next, our team started to consider the situation when both of the leaf springs are oscillating. And here there is an additional theta B that was not considered previously, as you can see here, because under this situation, the leaf spring, the other leaf spring does oscillate. And this is the differential equation that we came up in order to solve the differential equation listed here. However, since this differential equation, like you can see here, is too difficult for us to graph it out, and even using computer programs, therefore we do not have the symbolic solution to this differential equation. Instead, we use a numerical method to deduce the period. So we can, after using the numerical method to deduce the period, we can then compare the theoretical value with the experiment again. So with the theoretical value being 0.1475 seconds, the experimental result is 0.143 seconds, which there is a very comparatively small error within the comparison between the theoretical value and the experimental value. Then finally, I will discuss generally about the experiment and the relevant parameters that we investigated during the experiment. So for the first case, we investigated the symmetry of the magnets on the leaf strings. So here I would like to define the symmetry that we are discussing about. So symmetry in our experiment refers to this state when the magnetic dipole moment of the magnets on the both of the leaf strings are the same. So so under this condition, as the judges and the opponents can see in the graph, the magnets tend to oscillate in a uniform way compared to the next condition, which is the symmetry of magnets. So since we have established that this symmetry of the symmetry that we have discussed in our experiment is when under the condition when the magnetic dipole moment is the same. Here we investigate the condition when the magnetic dipole moment is different on the two leaf springs. And as from the comparison between the two charts showing the position of the magnets, you can see that the magnets does not oscillate in a ideal way, and then we also consider next I will be introducing the relevant parameter of length. So in this experiment, we also consider the difference in length, and by comparing the experimental results to the theoretical models, the models that we have established tends to be right, since there is only a small deviation between the theoretical value and the experimental value. And lastly, we also discussed the condition on. We also discussed the motion of the magnets under a different initial angle, and here again our model seems to be correct, since there is indeed the error between the deviation between the experimental results and the theoretical value is almost the same. And here is above is my presentation. Thank you.
Okay. Now let's have the opponent to ask questions.
Okay, so first of all, you guys took into account. Wait, can you state all the parameters that you tested?
The initial angles and the different magnetic dipole moment.
So you guys accounted for like the angle which the magnetic field was turning at, right?
Yes.
Okay. Did you guys? So you guys did not talk about the damping effect.
We neglected the damping effect during the experiment.
Did you guys consider using the Euler-Bernoulli principle or Euler-Bernoulli equation to model your this experiment, or you guys only use the torque, the magnetic torque?
You elaborate on the.
Okay, I'll talk about that later. Did you guys consider the external coupling of the magnets?
What do you mean by?
Oh, okay. Then we'll talk about that later. So you guys only talked about the torque. Did you talk about the restoring force of the leaf spring?
Yes, we have take that into consideration as I mentioned in my presentation that we did measure the recovery torque.
Okay. And for your setup, was the experiment on the same base? So like the base was all connected together, right? That connected to the leaf string. Okay. Wait. Did you guys consider the like frequency at which the of the wave of the oscillation?
Would you like to? Can you show me what we are referring to, or can we
Okay.
discuss later?
Yeah, we'll discuss later. And then, so.
Okay, the time is up. So you have 3 minutes to prepare for your presentation. 您有发那种类似草稿纸或者什么给？对。Okay, so Conan, please start with your report.
So, we're talking about the magnetic mechanical oscillator topic number 6. I'm Darren Z from No Rider. So, he already explained our problem topic. And so, what we think we should focus on is the disappearing beats as well as the external coupling, which the reporter did not talk much about. Okay, so for their observations, they have a good setup example and they showed their setup clearly, but they did not talk about the different selection of strips that may affect the motion of the, or the effect of the oscillations. and they had no normal mode observation. And so they had a differential equation theory for the torque and had a correction for the magnetic field angle, but they did not talk about like damping as well as external coupling, and they didn't consider the Euler-Bernoulli equation, which we think is very important. And so we saw in their experiments that they discussed about restoring force, and but they did not talk about like the magnetic force distance rotation as well as the external coupling of the two magnets, and they didn't discuss about. I didn't think they discussed about like the beat phenomenon that you see with the yeah. And so for their data analysis, I don't think they did much data analysis. So they didn't really talk about the initial movement of the non-perturbed magnet. They didn't have the FFT frequency. They didn't have anything about like the frequency of the oscillations, and they did not talk about like large oscillations. All right, we go on to our discussion. Okay, so first of all, I believe that you guys did not talk about you guys only tested one strip, right? You guys did not use different types of strip or different metal strips. Is that right?
Correct, but however we did consider the difference of the strip by including it to the K function that I had mentioned earlier.
Okay, but then how did you experiment with it?
Yes.
With the different resistivity or the different restoring force of the different types of strip?
I believe that the restoring force can be explained by the K function since indeed we didn't test different strips. However, we did evaluate how the strip behaves when it experiences external force.
Okay, so to make it clear, you guys did include it in your theory, but did not experiment with it. Alright. So, for the, can I see the slide for your correction of the field? I'm not too sure, because, I mean, it's your slide, right?
Your slide.
So did you guys consider the correction of the magnetic field angle?
Yes, we did by including it in the vector manipulations.
Can I see do you have it shown in a slide?
I'm not sure which slide are you referring to.
Oh, so, but you said you did do a correction of the magnetic field, right?
Yes.
The angle. So then you should know which one you're referring to.
So in here, here you can see that we included the phi angle and the alpha angle in order to correct the direction of the magnetic field.
Right, but then okay, so the problem with this is that I feel like your correction of the magnetic field is only like one line, right? Because so the magnetic field of a magnet goes out from the north pole to the south pole in many different, infinite different lines, right? So you guys only considered one line, I'm guessing.
We did consider the different directions by including that into the formula for F.
Can you explain more about the formula and how you corrected with it with multiple different magnetic field lines?
So the angle of the magnetic field line is already discussed in this, and here we use the magnetic dipole moment to incorporate that factor into the calculation.
So you say that you did. I feel like I don't see much about it. So I feel like you can work on creating a theory with a better correction for the magnetic field that accounts for the different magnetic field lines that come out of the magnet. And then so, did you guys consider? Okay, so I asked you about the base of your setup. So can I see your setup picture again?
we use the micrometer to fix the leaf string and then attach the magnet onto the top.
Okay, so this leaf spring is connected to one. Oh, so this is the leaf spring. They're connected to the same base then.
And they're connected by, they're fixed by like different micrometers, as you can see. Like,
So I think the topic statement actually says that it has to be on like a single base. So I feel like if you should do your experiment, you could do your experiment better if you have your everything on the same base.
So,
Like-
so are you saying that you think that the problem statement states that the base shouldn't be static and it should like oscillate with the magnet?
Oh, so here it says like the leaf string, secure the lower ends of two identical leaf strings to a non-magnetic base, so it has to be on the same base. So the reason, and then so if you do put it on the same magnetic base, then you can see an effect called external coupling, which like there are two different types of modes. So the leaf springs will have both move in the same direction as well as move in like opposite directions. But then because of external coupling, the base would actually move opposite to the motion of the oscillators because of conservation of energy. But then I feel like because you didn't connect it to the same base, a non-magnetic same base, I feel like you could not see the effect of external
So
coupling.
you mean that the base should not be static and it should like move along with the magnets?
Yeah.
Okay, so
Right.
indeed our experiment focused on the fixation of the base.
Okay. And so, so can you explain your slide on how you did experiments on like one oscillation at first, and then you put in the two afterwards, static one. So this equation is for the one, when you're only looking at one leaf string.
Yes.
And then, so can you explain what you changed from this to the external one?
So here we focused on the conditions where the other leaf string is static. However, we elaborated it and then like derived another like formula for the condition where when the other leaf string is like oscillating with the
Can I see your slide on your like oscillation theory, the theoretical oscillation? Wait, I think I saw another slide. Can you sorry, your experimentation. Yeah. So, did you look at the beat theory? So, I talked about the beat phenomenon where like the oscillation is like going like that, and then the amplitude becomes smaller and then larger. So, did you go in depth into looking why that happens? Do you have an explanation for it?
I believe that is caused by the damping effect. However, we didn't like provide a detailed derivation like we had.
Okay. And okay, so that effect I think you guys should look into as like the effect. So it gets larger because of the magnets moving together and the oscillations are larger. And then okay, so can we move on to the next experiments? Okay, wait. So I believe that you guys didn't look into like the frequency of your different the frequency of your different oscillations, right? So you guys only looked at the oscillation path for your experiments. Okay.
However, can you elaborate on what you mean by the frequency of the oscillation?
So the frequency of the oscillation is obviously the frequency is how often it oscillates, right? So you could look into the theory of how much it oscillates and how the two how the oscillation of one affects the other in terms of frequency, or how fast they're oscillating.
We did, I believe that we did include that in the discussion on the period.
On the period?
Yeah.
Oh,
Okay.
Okay, so this is your experimental data of when it's moving, right? When it's oscillating. So this is one of the leaf spring and this is the other.
Yes.
Okay. And so, can you explain why I can see that the amplitude here is smaller than the one here.
Why is the one is the amplitude of one particular leaf string smaller than the?
Yeah.
I believe that theoretically it should be the same in terms of amplitude. However, I believe that it is a human error during the experiment.
And then so I can also see that the frequency, so the frequency I was talking about is actually like this, where if you see this is more closely packed together, right?
Yeah.
So the frequency of this is greater than this because it's oscillating faster. And so I feel like you could go into look into why this phenomenon happens. And so there's a Euler-Bernoulli's formula equation that you can use to model this, which I think could be better than your equation. And so Euler-Bernoulli's formula is so I feel like you should split your theory into two parts. So one of the parts, your theory is mainly just one part looking into the oscillation, right? So I feel like you could look into how the leaf spring actually has a restoring force. So when the magnet is pushing on each other, the leaf spring is actually moving deflecting, and then when it deflects, there's a restoring force, right?
Yeah.
And so, okay.
I think we did discuss on that particular topic as we have considered there is a restoring torque here.
Restoring torque. Okay. So your torque in this place is your restoring force.
How the leaf string responds to it when external.
Wait, but then can you explain why you use torque? Because I thought the restoring force is just a force backwards, right?
Restoring force. I'm not sure what you mean by that.
Okay. Okay. So.
So unfortunately, the time is up. So opponent, please summarize your discussion in 1 minute.
Okay, so first we discussed the type of strips, and then we believe that the reporter should try multiple types of strips with different metals, because the restoring force of the different types of strips can affect how the movement and the oscillation, the frequencies, and all of that. So the reporter did talk about did include that in their theory, but didn't do experiments, which is bad, I believe. And they could also look into the external coupling effect, as their setup was not accurate in my opinion, because theirs was not in a base that would move, so that they could not see the external coupling effect. And they should also, they did not look into the B phenomenon, which is basically the frequency getting larger, or the amplitude getting larger and then smaller.
Okay, so the reviewer.
Okay, thanks for the reporter and opponent. At first, I want to ask that the reporter, do you think the damping should be considered?
I mean, our
Yes or
experiment.
no? Thank you. Okay, and the opponent,
Can you ask
do
the
you think
question?
the damping should be considered?
Yes, of
Okay.
course.
And second, I want to ask the reporter that do you think different type of springs will affect your results?
Different type of spring.
Yes.
You mean this one?
use?
Yes, I do.
Okay, and the opponent.
Yeah, of course.
And next I want to ask the reporter that do you think the magnetic field that the opponent mentioned, it should be maybe expressed as a function of space?
I do not believe since we regard this as a two-dimensional.
Okay. And the opponent
Wait,
should.
can you repeat your question?
Because you say that the magnetic field should be expressed as a function of space, like not only
Or
one.
maybe not. Yeah, yes.
And next I want to ask that reporter, do you think the two springs should be on the same base?
I mean, it's
Like yes or no?
according to the problem statement, yes.
Okay. And the
Yeah,
opponent.
the public statement says it, so we should do that.
And do you think that you should consider two leaves mutual motion instead of just one spring?
Yes, and I do. I believe I do discuss. I did discuss that.
Okay, so and the opponent?
Yeah.
And next I want to ask that, do you think that you should use torque in your theory? Do you think it is proper to use torque to explain your theory?
Yes, since our theoretical model and the experimental results does match up and there.
Okay, any
I
opponent?
believe you should probably use force.
Use force. Okay. And next I want to ask the opponent that, because in your presentation you mentioned that the initial movements of magnets should be
Yeah.
considered.
So of course the initial movement is the movement might
So
but
like how will it affect the results?
I did not see much initial movement, so it Yeah.
And the report, do you think it should be considered?
What do you mean by
The
that?
initial movements of magnets, like the opponent has mentioned in his presentation.
Do you mean the initial displacement of magnets? or
Yes.
Yes, I do.
Okay. And I want to ask the reporter that what do you think is the main parameters that will affect your results?
I believe that the main parameters that will affect my results are like the value of the magnetic dipole field and the distance between the two leaf strings and the type of leaf string.
Okay, and the opponents,
can you repeat?
like what is the main parameter that will affect the results?
Oh, there are a lot. So the material of the strip, the magnets, thickness, the magnetic force, and yeah.
Sorry, the time is up.
Okay, so
So prepare for your report. Please begin.
okay, so thank you for reporting opponent. So I'm a reviewer today. I'm going to review topic number 6, magnetic mechanical oscillator. So this is a problem statement that when you secure the two identical leaf springs, non-magnetically based enable report and are free to move. So the reporter's main focus will be the phenomenon and investigate the parameters and model and theories. So this is a summary and comments for the reporter. As for the theory, he mentioned oscillating of single leaf spring and also the magnetic torque for static and dynamic one. And for the experiments, he used the magnets, leaf spring, wooden base, camera, and tripod, and tracker to analyze the motion. And for the parameters, he mentioned the symmetry and also the length of springs and initial angle. So here's some of my comments for the reporter that I think he has proper experimental setup and can have simple definitive theory in comparison for the theoretical value. While some of my suggestions will be that maybe there can be analysis for the experimental result and units for the equations, and many parameters not defined, and lack of experiment behind the explanation behind the result and didn't have conclusion. And for the opponent, I think that he can find out some errors and we are understanding the reporter's reports. He can focus on the problem statement and mention the damping effects, restorative force, and frequency. Some suggestion will be that maybe there can be more data analysis discussion, and also because he mentioned Euler Bernoulli's law in his presentation, but he didn't discuss about it, I think they can discuss that. So here's a review for the discussion. First question is that how many types of leaf springs do you test? The reporter said only one. I think various strips should be tested since the elastic minus effects. And the second question is that do you consider the angle of magnetic field? The reporter said yes. I think that the magnetic field should be expressed as a function of the space, as the opponent said, as there are much more to discuss than angle. And the third is that the base of the spring is identical. The reporter said that they place on different spaces. And I think as the problem suggested that the two springs should be put on the same base. And the first question is that is it the connection between equations and data? And the reporter repeated his presentation. I think that detailed comparison between the theory and experiment should be made. And the fifth question is that explanation of the envelopes of the wave. And the reporter says it's a damping effect. And as the opponent has stated, we believe that it is a consequence of beat frequency. That's where the discussion can be made. And why is the amplitude smaller? And the reporter said that theoretically they should be the same. And I think further discussion can also be made that different frequencies should be investigated. So here's some of my questions. First is, should the damping be considered? Both of them say yes, and I also consider them that they should put the damping into the experiments. And the second is, can different springs affect? And both of them say yes. That I think a reporter should discuss about the motion between two different leaps. And the third question is that, should the magnetic field be considered as a function of space? That the reporter say it only has to be considered as a two-dimensional. As the opponent says that it should be considered like a function of space. And the fourth question is that it is proper to use torque to describe. And the reporter say yes, while the opponent said that force is sufficient. And the fifth question is that should initial displacement be considered? And both of them say yes, which I also think it should be considered into the experiments. And the sixth question is that what is the main parameter in the experiment? That opponent said about like the angles and the texture of the springs or the length of the springs. And the reporters and the opponent say it's the magnetic dipole. And here's some of the conclusion. For the missed points, I think that maybe they could discuss more about the initial movement of the springs and the Bernoulli laws that the opponent want to discuss, and also the beat frequency that should be discussed. And the concept revisits will be the parameters, experiment discussion, and the series. So here's my presentation.
So the reporter appreciates all the discussions on various topics brought up by the reviewer and the opponent. And here are my concluding remarks. So the reporter also believes that we should consider the damping effect during the oscillation and should have more discussion on that topic since it is quite insignificant. It is quite significant. It is observable from the graph shown on the slides previously. And although we did include the K function in our models, we should indeed include experiments on the different types of the strip. And this reporter also agreed that we should include more discussion on the beat phenomenon and also the discussion on the external coupling effect. However, the reporter thinks that it may be based on the problem statement since the problem statement stated that, simply stated that securing two identical leaf springs to a non-magnetic base, and did not mention that the base should be static. Therefore, the reporter agrees that this can be a topic that's worthwhile discussing. However, the reporter doubts that if it belongs to the scope of this debate. And thank you.
Okay. So let's now move on to Julie's question. Any question from the jury?
Yes.
Let me start with the reporter. Before my question, I'd like to comment a little bit. It's just oscillation or harmonic oscillation is one of the basic, probably the most important problem in mechanics or even in physics. So I guess when we talk about this kind of problem, we expect to hear some basic fundamental. Okay, he said, the damping or the field-driven or coupled oscillation and so on. I was a little bit disappointed. I guess just mentioned a lot of just very complicated, not just straightforward model. For example, if we consider if there is only one spring, the problem has two springs. If there is only one spring, you investigate one spring. What would be different from one spring to two springs?
So, is there any external magnetic field?
Just try to use more like I said, physics, damping, coupled equation, and so on.
Since if there's only one spring, it will not experience any repel forces from the another spring, which is inclusive in the problem statement. So I think the oscillation will last longer, and the modes of oscillation will be simpler.
So obviously, when you only have one leaf spring, you don't have the magnetic force of the other magnet affecting the first one. So you wouldn't see a coupling effect. You only see, you only have the restorative force of the spring.
So what would happen
if you have two?
one spring? If you
If
consider
you only have one
damping,
spring?
if you consider damping, what would happen?
Well, just gets the oscillation would probably get smaller.
And the
So
difference between one and two.
Yes, I think that's because when you try to talk about the motion of the two springs, then there should be discussed about the two magnetic force between others. So I think that the oscillations will be longer, since they will affect others and increase the oscillation.
Any other question? I have a question for the opponent. You keep mentioning Euler-Bernoulli equation or
Yeah.
Euler-Bernoulli formula.
Yeah.
Could you explain what it is?
So the Euler-Bernoulli equation is a differential equation that basically can model the restoring force of a leaf spring. And so it's a differential equation, so when you solve it, you're able to get you're basically able to get the force of the restoring force, given that you have a force that pushes on it. So it's basically how much restoring force it has to push back.
So because since they didn't discuss about that law, but from the opponent's presentation, I think it is like he said about the storing force that will push back the motion.
So that's just Newton's second law.
So the equation, it has to do with how the metal is created. So the metal, because the metal strip stays together, but then when you push it, the whole thing stays together. But in some way, it's similar to Newton's second law, I guess. The restoring force, because the leaf spring is like a magnet that has its own like sorry, I don't really know how to explain it.
Okay. So the time is up. So let's just move on to the grading session. So let's break for the reporter. Four, 5, 7, 4, and 6. Now let's move on for the opponent. 5, 7, 7, 6, and 7. Finally, for the reviewer, 7, 7, 8, 7, and 7. So any remarks from the jury about this physics one? If there is no further comment, then let's end this stage. Let's return in 10 minutes.
So, okay, Team Galileo wants to challenge with problem number 2, oscillating speed.
The reporter accepts the challenge.
Okay. Problem number 2, accepted. So again, please write down the name of your presenter on the blackboard.
Okay, so today we'll be talking about the oscillating sphere. I'm Darren Z from Nolan Ivy. Okay, so the problem statement says that a light sphere with a conducting surface is suspended from a thin wire when the sphere is rotated about its vertical axis, thereby twisting the wire, and then released, it starts to oscillate. Investigate how the presence of the magnetic field affects the motion. So you can see there the phenomenon investigation. And so our focuses are the magnetic damping, the magnetic uniformity, and the surface of the magnet. Okay, so for the phenomenon investigation, so we have our, so what happens in this problem is that we have a magnetic field like this, and this creates an electric field caused by the movement of the electrons, which creates eddy currents, forms in circular motion, and this current causes the de-spinning of the torque when you spin the ball. So for defining, so we define the axes on our setup as the Z is the direction of the magnets, Y is into the page, and X is up into the yeah. So when we're looking at the direction of the magnet, we see here that like when the ball spins, the current is going up because the magnetic field is going into the page. So if we use the right hand rule, we can see that current is going up. And so when the ball spins the other way, the current is going down. And then for that diagram, we're looking at the side of it where the magnets are on the side. And so what we see here is that when the ball is spinning, we can see that the direction of the flow and the current is going in a circular motion. And then here is the top view of the ball. So when we're looking down on the ball, the magnetic field is going from one side to the other, and so with right hand rule, we can tell that the current is going from up into the page and down the other side. So for the orientation of magnetic field, we believe that the magnetic field is parallel to the rotational axis. When that happens, there is no torque or damping, but when the magnetic field is perpendicular to the rotational axis, there is torque or damping. And when the magnetic field, either uniform or non-uniform, is perpendicular to the axis of the rotation, we can observe underdamping, which is the slowing of back and forth motion, which allows oscillation, and which is described as this equation and that yeah. So for our setup, we have two magnets here. This is our first setup. We have two magnets with a clamp. With a clamp on the wire with a ball here. And then so our setup 2 is when the magnetic field is parallel to the wire and the ball. So we don't have a Helmholtz coil, so we use two solenoids to arrange in the form of a Helmholtz coil to create a uniform magnetic field. And so for our perpendicular magnetic field setup, it looks like the previous one, except now the solenoids are turned. And so for our data collection, we had a vernier probe that for calculating the magnetic field, and we put it through. And then so this is the graph that you can see. And so we use the peak graph for the magnetic field. And so for the ball movement and tracking, we use trackers to track the ball movement and put it into a Python program. And then we find this. So this is our motion, as you can see, of the ball. And so the example fits the graph really well. And then so for uniform and non-uniform magnetic fields, there should be little difference between the effects of the uniform and non-uniform magnetic field on damping. And gradient of the magnetic field shouldn't affect the damping because it is already built into the gradient as the shape is 3D and spherical, where the current goes up one side and down the other. And so for our experiment, we experimented with uniform magnetic field and non-uniform magnetic field and found that the difference between the two in terms of damping is very small, so we just use the non-uniform magnetic field for our experiments. So for our assumptions, so the conducting sphere of the conducting surface of the sphere is entirely smooth, and there's only torsional motion and no pendulum motion because that's what we did for our trials. And the glue attaching the wire to the sphere is negligible. And so for our damping, so the theoretical model for additional damping to the magnetic field is this standard damped harmonic oscillator equation. And then so we use the EMF as well as the current and plug it into the torque to find the new equation. So yeah, and then so this is our standard damped harmonic oscillator with edges. And so for a perpendicular solid sphere, we actually use the velocity as well as the electric field to, and then we changed it slightly. Oh, we plug the velocity into the electric field, and then found the current density, which we then use to find the force, and then the torque later on. But these are like per unit volume, so then we had to integrate it to find the actual torque, which is the N, which is N, yeah. And so once we did that, we found that the alpha constant for our previous equation was roughly 2 pi over 15 for a solid sphere. And so for the governing equation for the experiments, we have gamma here as a damping constant, and then so we have this previous equation, which is the torque, plus the gamma naught, which is the damping that's already present without the magnetic field. And so for our experiments, we're trying to prove the proportionality of these values. And so in our experiment, we tested the parallel magnetic field, and we found that there wasn't a big difference between the magnetic field. So we tried 0 millitesla in the solenoid magnetic field and 6.2 millitesla, and found that the damping constant didn't change much. So we believe that the parallel magnetic field does not affect the damping. And so for the experiments, we varied the different materials. So we had aluminum, brass, and tin. And so we're trying to prove this theory. So this is the graph we have with this one being the aluminum, and then this one being the brass, and this one being the tin. And so, we have our resistance down here. So the damping constant is inversely proportional to the resistance, and so we found that as the slope increases, the resistance is decreasing. So the resistance of the tin is actually, I think, the highest, with the aluminum being the lowest resistivity, and that matches with our theory. So when we vary the radius, we found that as the radius increases, we used the copper ball for this experiment, and found that when we increase the radius, the slope increases. So that also fits our theory. And so we also tried ferromagnets, which so the ferromagnet we use is a steel ball, and so the steel ball, the slope is 0.013, which is, and it had a resistance between the tin and the linear brass, so it matches with the theory well. But then, so the ferromagnets can have hysteresis, where it creates like a permanent dipole, and that's like unaccounted for, and it's impossible for us to account for, so we did not look into that a lot. Yeah. And so in conclusion, the motion in a magnetic field creates current. It induces an electric field and creates a current, and the current experiences a force. And our experimental data is modeled by the linear equation as given, with the damping constant equal to this value and the initial damping constant without magnetic field. The magnetic field is parallel to the ball. When the magnetic field is parallel to the ball, it results in no damping, and perpendicular results in damping. And an increase in surface resistance and radius of the ball increases the damping. And so damping increases with the strength of the magnetic field and radius of the ball. And so for the show, okay, and so we also proved the theoretical proportionality here in our experiments. Thank you.
Okay, first of all, thank you for your presentation, and I have a few questions about your presentation. Please turn to page 9. Okay, so yes, 9, please. Okay, so here you show a formula that right here is gamma over 2. So did you obtain the number 2 theoretically or theoretically?
Theoretically.
Okay, so now please turn to page 10, next page. So you have a wire here, right?
Yeah.
So did you measure the elastic coefficients of the wire?
I don't think so.
Okay, now please turn to page after 20, where you did not show the index. Okay, right here. What is the meaning of this epsilon right here?
That's not EMF.
EMF. Okay, you mean electromotive force.
Yeah.
Okay, the next page. Okay, so here, is that E electric field?
Yes.
Okay. Yeah, so now please turn to page 20. Excuse me, 26, please. 26. Yes. So can you restate what are the meaning of the horizontal and vertical axis?
So the horizontal axis is I think we graph the gamma.
Okay, thank you. We'll
So
leave
the
that to
gamma
our
and the-
later discussion.
field.
And one last question is, did you consider a uniform magnetic field in your experiments?
Yes. We explained.
Thank you. competitors. I'm the opponent from Team Galileo, and the topic of the opposing today is question 2 oscillating sphere. And this is the problem statements. And we believe that the main focus of this presentation should be the conducting surface and how the magnetic field can affect the motion. And the main focus mentioned by the reporter's team is stated that the main focus are the magnetic density, magnetic uniformity, and surface. And the first one is the core of this phenomenon, and the second one, magnetic uniformity, guarantees the results of the experiments. And the third one, surface, are control parameters. So which means that the opponent believes that this part is pretty well. And this is the outline of the reporter's report. For the theory parts, he introduced the conceptions of eddy currents, and he used the right-hand rule to modify the orientation of magnetic field, and he mentions that the motion is kind of under damping. And for the experiment parts, for the tools, he has a wire, and he tested balls with different materials, as he mentions, aluminum and some other metals. And for the parameters, he tested the magnetic field orientation, which was parallel and perpendicular to the rotational axis. And the results were quite different. And they also have varying materials and varying radius that guarantees that kind of different parameters. And for the analysis, they use a 3-axis field sensor to analyze the strengthening of the magnetic field, and they use Stratford Python for the motion analysis. And the conclusion they reached, the first one is the motion creates current, and current experience force. And the second one is a parallel magnetic field will have no damping effect. And the third one, the damping increases with radius of the ball and magnetic field. And here are some comments for the reporter. First of all, he has thorough experimental results, and his data analysis for damping was quite in detail, and he has very fluent presentation. And he also rich in parameters like radius and orientation and materials. And for the suggestions, first of all, we believe that the theory was kind of like a quantitative theory, and also the connection between the equations wasn't clearly stated, and also there wasn't explanation for many symbols that may cause some misunderstanding of the when understanding the presentation. So these will be the discussion points in our later discussion. For the phenomenon, we will discuss the time oscillation and put it in categories, and the ELM of the phenomenon. And for the theory parts, we will discuss the electromagnetic induction on the sphere in detail, and the presence of the induced currents and direction of the induced currents, and the electromotive force. And for the experiment parts, for the experimental parameters and basic control parameters, and basically these. And the conclusion, which we just mentioned. So I'd like to start my discussion with the guidelines to start my discussion now. Okay, so now can you please turn to page 20. So here, it seems that your equation of motion, you consider in 3 terms, right? You have the angular acceleration and angular speed term and the angular displacement term.
Yeah.
Okay. So can you briefly explain how did you derive this equation?
Which the
No, I mean this one, the very top one.
Oh, I mean it's just theta is just it's the standard band harmonic oscillating.
Okay, so let me restate my question. What does omega naught mean in your presentation?
Omega naught is
Is it the initial angular speed,
I think
or is
yeah
it just?
the initial angular speed because we're turning the ball, right?
Okay. And you also have the term gamma, and did you combine the air resistance force with your magnetic damping effects that you reduce the all terms into a gamma?
We did not. I think we did not consider air resistance.
Okay. Now please turn to page on the pages on the theories. Okay.
The theories.
Yes. The page that you calculate the force and torque.
Oh, sure. This one.
Yes. Yes, this one. So from this results here, we can see that this F force or
N is the torque, the total torque.
okay, so N is a total torque. So we can see from your equation that it seems that your total net torque is proportional to the angular speed.
Yeah.
Right here. So so indeed the angular the damping caused by the magnetic field, the angular acceleration is indeed proportional to the angular speed. So is that the reason why you combine the term into your equation of motion? Since we all know that the resistance caused by the air, which experimentally is also proportional to the angular speed.
I don't think we consider the air resistance because if the angular speed is because of the torque.
Okay, so is that term of the gamma, is that the factor caused by the damping?
You mean gamma? Is
Yes,
gamma
the gamma. That term gamma.
So
zero delta.
gamma is what we call the damping constant.
We call it damping constant, so you do consider it as your damping.
Yes.
Okay, thank you. And now please turn to page, the previous page that shows the electromotive force, EMFs.
Oh,
So this one.
or the one before that.
Okay, this one. So here you have that epsilon equals to VBR, and can you briefly explain that?
Okay, so epsilon. So this is the equation for EMF.
Yes.
Yeah. So we turn the velocity into R omega because the velocity is equal to the radius.
Okay, so since your formula that epsilon equals to VBR, so since when a sphere is rotating, can we go to the blackboard? Since the whole sphere, they have to move with the same angular speed, otherwise the ball would have a fall, and it rotates with angular speed. Okay.
Yeah.
Okay. So which we mean here that here it has the V maximum when the radius when it is at the equatorial plane, right?
Yes.
Yes. But when we're talking about here,
Oh, right.
yes, there is
So-
another velocity. So how do you consider the electromotive force under different conditions?
I think we assumed that it was. I believe that we should include it in our theory, but we assumed that this did not affect it. Was not a big. Did not have a big effect on our. Phenomenon. So we did not consider it.
So this is my basic understanding of this of your presentation. First, you have motion, which is a relative motion between for the ball and the magnets. The ball is moving, is
Yes,
rotating
it's
the
rotating.
magnets.
Yeah.
So there are basically two kinds of EMFs: the induced EMF and motional EMF.
Yeah.
So here we're considering motional EMF.
Yeah.
So you have motional EMF, and therefore there is going to be an induced current.
Yes.
Okay. So yes, so to this point, I think there should be a correction since this is the reason why you have the induced currents, and the induced currents affect directly can interact with the magnetic field, and that's why you have the torque. So I think this part should be verified since this part is
I believe we could verify that.
And please, okay, so please, let's go back to this. Okay, so please turn to the next page. Okay, here you stated that the electric field equals to the cross products of the velocity and the magnetic field. Can you explain that to me?
Oh, so the cross product is just the velocity. Wait, so what do you want me to explain?
Well, since when my first impression when I look at this, when I look at this equation, what I think of was the Lorentz force law. It can be applied when a charged particle moves through a magnetic field.
Right,
So what I'm wondering here is, since we have F equals to QE plus QV cross B. Yes, so the unit here is right, but what I want to hear is that you stated that E and V cross B, they are the same, and since it's vector quantity, the direction is also the same.
So
the direction
what
of
is your question?
Okay, my question is, how do you derive this one? Because if we intuitively look at the formula, since we just agreed that we derive the formula from the Lorentz law. And it seems that if you want to have the conclusion that the electric field equals to this term, first of all, you need that force equals 0. And then you cross out this Q term, and you have the results that E equals to D plus B. But here, there will always exist a minus term, right?
Right. Yeah.
So can you explain how to derive the equation?
Wait, I think we have a minus term in the equation. It was like on the second step.
Okay, thank you. And I'm afraid we have to move on to the experiment part.
Okay.
So now please turn to page 10. Okay, so here, can you tell me what the size of your ball is? The radius of the ball.
So we did multiple radiuses as we shown in one of our experimental slides.
And as you stated in your presentation, you used the sinusoidal coils to create a
yes.
relatively. However, it is not always uniform everywhere in that coil. When you have the coil, let's assume it wraps like this.
Yeah.
It is only uniform at the very center, and when at the edges there is a curvature, and then you have to take that into your consideration.
Okay. So I believe that does not affect it too much because we have the ball in the middle.
So is the size of the ball relatively small to the coil?
I would say so.
Okay, thank you. And now please turn to page 28. Okay, so here you show that you've shown your experimental results that the horizontal axis is
The magnetic field squared over that.
okay. So is I the induced current?
Oh yeah, yeah.
Okay. So how did you measure your induced current on the sphere?
I think these were we measured it. I'm not too sure.
Okay, okay, that's fine. So based on your experimental results, it seems that the gamma is proportional to the gamma naught, right?
Yes.
And how can you relate that back to your equation of motion?
Wait, this is our so we had an equation with the gamma in it. So wait, I don't get what you mean because we have the gamma has to.
Okay, I believe I've asked an appropriate question, so let's just move on. Okay, so please move back to page 9. Yes, 9. Okay, so yes, here you mentioned that you derived this too theoretically, and can you tell me how?
Wait, this is just the equation for the.
Yes, but how? Yes, but how can you make sure that it is 2, not any other number? And plus, if we consider this, there should contain a time term in your exponential function, so that
Is the time not this?
yes, but it is also, but it should be considered in that exponential term if we're talking about the decay.
But we're just looking at the oscillation, right? But so the gamma is just we are only looking at the derivative equation for gamma.
Yes, but if that is the case, then that is the constant, then it wouldn't be a damped oscillation.
Well,
Okay.
I'm sorry, I have to stop you because the time is up. Yeah, please summarize your discussion.
During the discussion, we had discussed multiple discussions over the theory and the experiment. And for the theory parts, your opponent thinks the reporter didn't handle the expression of the electromotive force, since they also have to consider that different parts on the sphere may have a different velocity, since they all have the same omega, and v equals to omega r. So the opponent would suggest the reporter to take that into consideration. And for the experiment part, as the graph that the reporter demonstrated, the size of the sphere is relatively or sometimes even bigger than the coil. So which means that the magnetic field is not always uniform. And the opponent suggested for it to reduce the size of the ball so that it is actually placed in a uniform magnetic field as he suggested in his theory.
So you're finished?
Yes.
Okay, thank you. Yeah, so now let's move on to reviewer's question.
Okay, so first my question is for both the reporter and the opponent. I would like to ask if there is no magnetic field in the experiment, like just a ball rotating, and what would the damping be? Where would the damping come from?
Well, the damping is just coming from the wire or whatever it's attached to.
So it's just only from the wire.
Basically.
Well, I believe the damping comes from the air resistance.
So is it only air resistance, or you will consider what?
Well, since the wire is not compressed, so I believe there will be some thermal loss when the wire rotates and when it's experiencing motion.
Okay, got it. And so same to for the opponent, just as you just mentioned, their air friction and the wire would cause the damping. And I would like to ask how significant may the damping effect caused by air resistance and the wire compared to the damping effect caused by the magnetic field?
Well, since the wire we can approximate it view as let's say a Basic law. So which means the torque that it gives to the sphere, it would give back and it goes back into the other direction. So, but however, on the other hand, the air only takes energy away from the sphere. So I believe that the effects caused by the air damping is more significant in the situation in which the magnetic field is applied.
Okay, thank you. Okay, we'll speak. And now for the reporter, as you just mentioned, one of your focus is about the surface, but I'm not sure if I get it in your presentation. Yes, about the surface part.
So I don't think we have we tested the surface, but we didn't put it on this slide. We have certain information in the appendix relating to that. We took it out of the
So I guess it's not shown on the presentation.
Yes.
Okay, got it. And I would like to ask, saying for the reporter, can you define all the terms of the angle, like in, here's a page you got a bunch of formula, or is it possible for you to find it, like immediately? Yes, just like their thetas and phis,
So
I guess.
theta, so this is just the angular position, the angular velocity, and the angular acceleration.
Okay, got it. And so, lastly, I'll just ask the opponent that the first question I just mentioned is how significant it would be for.
Sorry. Okay, the time is up. So please prepare for the presentation. Please proceed with your presentation.
Honorable judges and fellow debaters, I'm the reviewer from Team Uli Kanhua, and I'm Typt. Sorry, Chris. Okay, so first, here's the topic of problem number 2, oscillating sphere, and the focus which mentioned by the reporter is first the magnetic damping, which is probably the most significant topic we're talking about in this problem. And the magnetic uniformity and the surface, which the reporter unfortunately didn't elaborate on that much. So first, for the phenomenon the reporter mentioned, the magnetic field, which causes electric field, will form eddy currents and which cause damping to the sphere which is hanging on the wire. And the theory is the movement of the sphere in the magnetic field will cause damping by the eddy currents which was mentioned before. And for the experiment, the uniform magnetic field and just various material such as aluminum, brass, but same, I don't think that is elaborate much on the reporter's presentation. So for the pros and cons for the reporter, it clearly observed the phenomenon with illustration, although it's quite confusing for the labeling for the axis. But the experiment to test different parameters are also one of he did well, but the lack of explanation of the equation is kind of a minus. And for the opponent, he clearly pointed out the missing points which is not considered by the reporter, and also where the equations that is not clearly explained while the reporter is presenting. And sorry, I'm putting like wrong place. And the loud and clear is a big plus for it. So first discussion, this magnet means, and well, the reporter just said it's not considered. For discussion 2, like there's some terms that are not elaborated well in the whole presentation, and I'm glad that the opponent helps me to get on for the whole presentation more in the discussions, and like what gamma means and the EMF on different conditions. And I would like to focus on the last topic, which is here, how is it derived to the 2? And it's unfortunate that they can complete the whole discussion, but for me, that should be a little bit mistake for a reporter, because talking about the whole theory, the reporter first mentioned he ignored the air resistance from the air resistance which caused damping, and also the thin wire which caused damping. And that is probably like, I don't think it accounts that small that you can ignore it, since just as what the opponent mentioned, the air resistance caused damping. It accounts for much for the whole phenomenon. So
I'm afraid that the theory is not very complete for the whole presentation, and that will be end of my review. Thank you.
Okay. Now let's take question from the viewer. Oh, sorry, there's concluding remark from the reporter.
So we did not consider air resistance because we thought it was like, it was not, the effect was not that big. And so the opponent talked about the page 20, the explanation and derivation of the equation. And so we said that the gamma is a damping constant, and we should include like additional velocity into our equation. But then we also assumed that this vector was not significant. And so on page 22, the opponent talked about the net torque being proportional to the angular speed. The opponent took into account air resistance, but I believe it's just the angular speed. And so we also talked about verifying E and F. And I believe that the opponent, we should take in what the opponent said about the E and F and the induced current part. And so the derivation of the Lorentz force, we believe that we did add a negative, but just after that equation part. And so we also clarified the graph at 28 and how we measured the gamma. And so the opponent was asking about the gamma and the gamma naught, but I believe the gamma is just the gamma, the damping constant. And then on page 9, oh wait, okay. And the opponent also talked about how the ball was insufficient in containing a magnetic field, but since our ball wasn't that big, I believe that it did not have much effect on our experiment. Thank you.
Okay. Now let's have questions from the jury members. Yes.
I'd like to ask, you mentioned on your board is that he doesn't have quantitative derivation.
Yes, I did.
What do you mean by that?
Well, quantitative here, I mean the, maybe I misused the word because I was trying to say that it was to plug the real results into the equations you demonstrated. So maybe I misused the word.
So why don't you have quantitative derivation?
Wait, I thought we did have quantitative. Oh, we had the quantitative theory for how we got to the gamma constant. Right.
How long would it take to stop the oscillation?
How long would it
In your
take?
experiment?
When we turn the ball, right? So the ball doesn't the oscillation start immediately after the ball starts to move?
How long would it take, roughly?
The start? We
Time. How long would it take to stop?
to start oscillating as in
Stop.
oh, stop oscillating. Roughly, I don't think we looked into that. Yeah, we just because we measured the how much it was turning and the motion of the ball only.
You didn't look at it.
Yeah.
So what does the damping mean?
Damping means, you mean in the whole theory?
In the oscillation issue, what does damping mean?
Well, in my opinion, so first, I would like to talk about the condition when it's not placed in the magnetic field.
Damping is very short.
So first, there will be air resistance, and next will be the wire.
Resistance, damping is resistance.
Yes.
So if you want to stop the motion in a shorter time, what can you do?
Of course, to put on more forces to reduce the whole motion, which is also refers to resistance. So in the phenomenon, which means the electric field, which passing through the sphere, would generate a force which slowing down the whole motion, the damping.
Have you heard about overdamp?
Yes.
What does that mean?
Over damping, so, wait,
Okay.
Okay, any other question from the member? I have one question for the reporter. Did you prepare this slides yourself, or do you borrow it from someone else?
I did take it from my teammate, yes.
Your teammate
Yes,
or other teammates?
other, from our same school.
From your same school,
Yeah,
but not
so, yeah,
your own team,
yeah.
right?
Or we worked together on it.
But
yeah.
you didn't prepare the slides yourself. The reason I ask is that when you show your last page of your presentation,
Yes.
I saw all-nighter, not no-nighter,
Yes,
right? So you borrow it from someone else, not on your team.
yes.
Okay,
Yeah.
okay? No other questions? Are you all ready? Starting from me. 3, 7, 6, 5, and 7. So now for the opponent. 8, 9, 8, 7, and 8. Finally, for the reviewer. 6, 7, 5, 6, and 7. Okay, so the reason I gave you a 3 instead of 5 is that you didn't prepare the slides yourself. I don't think that's the right thing to do. You can, of course, you can work together and you can discuss, but you should prepare the slides yourself. Okay, so let's conclude this stage. Let's return in 10 minutes.
We'd like to challenge problem number 1, fractal fingers.
Number 1. You accept? Yes, you accept. Problem number 1. So please write down the names of your presenters for each team. I would like to remind all the team members there are laser pointer prepared for you on the desk. So please use it because it will be much easier for us to follow what you are talking about.
Okay, so I'm the reporter from Team Galileo, and I'm going to report topic number 1, fractal fingers. So this is the problem statement that when you deposit a droplet of an alcohol mixture onto diluted acrylic paint, then you can see the fractal fingers. So in this problem, I'm going to focus on first is the geometry to see different fractal extent and looks of fractal fingers, and the second is dynamics to see the growing speed, length, and area of the fingers. And so here's the observation. First, we found that there will be constant diffusing motion from the center, and while it is diffusing, the fractal fingers will start to appear. And then it will keep spreading until diffusing and fractal motion both stop, which we watch from camera. So it will have diffusing motion and go through fractal motion, and both of them will stop. So first observation is the purpose of alcohol. So first we do with different aiding here, found that alcohol will be crucial to be added into mixture. And next we do different proportion of mixture. We found that when adding more alcohol, it will become fractal. And then next is the purpose of diluted acrylic paints. We found that when we add more water into the acrylic paints, the fingers will become longer and more complicated. And last is the different dropping speed, which we found that when the dropping speed is faster, the fingers will also grow faster too. So here's my definition of fractal fingers. So a fractal will be a geometry shape that has self-similarity in different scales, like you can see from the simulation for fractal and the experiment of my fractal fingers. So my fractal fingers will be described as a finger's finger. So here's a separate different phase of fractal fingering. First is the diffusion motion. That's it will first caused by the gravitational effect, and then it will start by a Marconi flow and stop with when they have certain surface tension. And for the fractal motion, and so it is caused by segmental instability, and that's it will caused by perturbation and viscosity. Okay, so first is the diffusion that is caused by gravitational effects, and it's because that the surface tension wouldn't be strong enough to hold the droplet, so it will become flatter. And next is the diffusion, and it is when, because of the Marconi effect, that will start the diffusion. That's the center of the droplet is thicker, so it will evaporate slower, which has lower surface tension, and instead, at the rim part, it will have higher surface tension. And so you can see from the picture that Marconi flow keeps appearing from the center. And it is when the surface tension between air and mixture cosine theta plus the surface tension between acrylic paints and mixture cosine phi equals to the surface tension between air and acrylic paints, it will stop diffusing. And next is the comparison, because since I'm going to use halogen cell for my theory. Let's first we discuss about the pressure. In halogen cell, it will be board and board. In my experiment, I will change the upper acrylic board into air. And sorry. And next is the initial velocity. So the halogen cell is injected by siren, while in my experiment, it will be dropping velocity from pipe K. And here's a Navier-Stokes equation which I solved Newtonian fluid for later the Darcy's law. So the blue one is inertia, which can be equals to gravity force plus pressure gradients and viscous force. So here's couple nonlinear partial differential equations which I will use in later console. And first the continuity equation which shows the conservation of mass. And Darcy's law shows the concentration of momentum, and the convection diffusion equation shows that a mass that goes through a convection will have diffusion. And so here's Darcy's law. When the flow is in porous media, the motion will be attributed to Darcy's law, which you can see the instantaneous flux is proportional to the pressure difference. And because of the incompressibility of the flow in Darcy's law, it gives out an unperturbed pressure field, which P1 and P2 are two different phase pressure fields. and we mention the pressure field the interface, it can give on the equation 3. And when mu2 is higher than mu1, which fits our experiment, it leads to growth of perturbation. In this case, the equation can be rectified into equation 4, which plus the perturbation part. So you can see that from the equation 4, the growing rates will be affected by initial speed viscosity difference and eta of the viscosity. So we use COMSOL to analyze that, and here's a review for equation used in COMSOL. And here's the operation screen and parameters. In COMSOL simulation, we simulate a two-dimensional display, which surface tension has been involved in. So here's the experimental setup that I do my experiment on an acrylic board, and I use a stand to hold the pipette, and the pipette to control the amount of each droplets. And then I use a constant temperature batch to maintain the temperature of the fluids of acrylic paints and water-based ink being as 20 degrees. And first experiment is that I change the concentration of acrylic paints. And in this, we measure the first is the geometry, second is the maximum length of fingers, and the third is the growing speed of the droplets. So first we run with COMSOL, and we found that the R represents the viscosity difference, and when R equals to 0 means that there is no viscosity difference, there wouldn't be fractal fingers. When the R increases, the fingers will get longer and more complicated. So here's a comparison between experiment and model. So from the equation down there, you can see when the mu2's value change and also consider the perturbation, that's the COMSOL simulation fits our experiments. And next, I'm going to explain why there is a white ring you can see around the center ink. And it is because that surface tension will cause this cohesion, which means the ink will stay in the center while other ink will still go out to have fractal fingers. So you can see from the fingers that it will go clear to blurry when you add more water, and the structure will go simple to complicated, and back to simple since the water will dilute the end of fingers. So next is the maximum length of fingers, which I define as the length between the center to the rim and minus the center to the inner ink. So I use image J to measure that, and we found that when adding more water, the maximum length will be bigger. And you can see that here, the error bar will get bigger. And it is because the water will dilute the end of fingers, so it will depend on how much ink can go to the fingers. And next is the growing speed, which I use tracker to analyze that. And the delta D will represent the position to the fingers and minus the position to the inner ink. And we found that when we add 1.5 grams of water into 2 grams of paint, the growing speed difference of the rim and center ink is not significant. And also that when adding more water, growing speed will get bigger. So here's a comparison with the equation, and because of when adding water, the growing speed will get bigger, so the equation fits our experiments. And next is the experiment that I change the concentration of ink alcohol mixture, which will change the effects of Marangoni flow. So in this experiment, we are going to measure first is the geometry, and the second is the growing speed of the droplets. So from here, you can see that we separate the geometry into 3 different types. First is the regular ring, and next is the floor-like ring, and this is a fractal finger ring. So when alcohol to ink is 5:1, it fits our definition of fractal. And so to prove that Marangoni flow is caused by evaporation of alcohol, we do an ink-water mixture. You can find that it has a fractal-like ring but no diffusion. So it will first, because of gravitational effects, then pass Marangoni flow, and the rest go to the fractal-like motion. And then here we analyze the growing speed of the droplets, and we also use tracker to analyze that. So we found that when we add more alcohol into the mixture, the growing speed will be faster. It is because that since the Marangoni flow is caused by different evaporative speed of the rim and center, so when there is less alcohol, the evaporation difference wouldn't be significant enough. And you can find that when the proportion of alcohol to ink is 2:1, the growing speed seems to have a big difference from the other. And here's our conclusion that when the concentration of mixture can have fractal fingers, the growing speed will be slow. And the last one is that we change the speed of dropping droplets, which will change the initial speed U0. So in this experiment, we are going to measure first is the growing speed, and the second is the area of the droplets. So here we also use tracker to analyze that. And you can find that since the growing speed is proportional to U0, so when dropping speed gets bigger, the growing speed of the droplets and also the area will also get faster. But you can find that here, the growing speed will be slower over time. It is because that we have to consider the growing perturbation in our equation. And so here we compare with COMSOL, and you can find that actually when it is fast speed, the fingers will grow faster, and so it fits our experiments. So here's the conclusion. first for the theory. You can see for the diffusion part, it will start Marangoni effect, which is the difference evaporate speed of the alcohol, and it will end when they have the certain subtension between air, acrylic and mixture. And then for the fractal fingering part, it is caused by, as I have explained, segmental instability, which will cause by relation in viscosity and perturbation. And then this is the first experiment that I changed the concentration of acrylic paints. And we found that when adding water, fingers will go clear to blurry, and the structure of it will be contemplated when the concentration is around 2.5 to 3 grams of water plus 2 grams of acrylic paints. And next is that we found that when adding more water, lens will get bigger. And the third is that when adding more water, the growing speed will also get bigger too. And the second experiment is the concentration of mixture. So first, since the alcohol to ink is 5:1, it will fit our definition of fractal. And the second is that when adding more alcohol into a mixture, growing speed will get bigger too. And the next experiment is the dropping speed of the droplets. That we found when dropping speed gets bigger, growing speed will also get bigger too. And as well as the area of the droplets will also get bigger too. So this is my presentation. Thank you.
Now, it's a question from the opponent.
Opponents. I am the opponent from Typt, and here I have some questions for the reporter. So first, since in the problem statement it doesn't demonstrate what kind of alcohol should be used in the experiment.
Yes, so I use S602 in my experiment.
Okay, so I have to test others.
I didn't text other because I want to focus on like the problem statement say the finger structure.
Do you think others?
Well, I think that if it is different alcohol, it will also affect the results.
Okay, thank you. So, can you restate again how you define the finger starting to grow?
Fingers start to grow.
Yes.
So, because as my definition of fractal, it will be there is an initial finger and there is another finger grow from the initial finger. So I will see that when there is like I have said for the definition of fractal, then I define that as where the fingers will grow.
Okay. Can you describe how you describe the fractal extent?
Okay, so as you can see that, and there's a page I show different extent of fingers.
Can you enlarge those?
Make the slide bigger, make it full screen. Yeah, I'm sorry, the time is up. You can continue later.
Okay, sure.
So prepare for the presentation. please begin with your presentation.
So, honorable judges and worthy competitors, good evening. Today I'm from Team Ulikanhua, and today I'm gonna restate the problem number one fractal figures. Okay, so start with the problem statement. This phenomenon is to observe if a droplet of an alcohol mixture is deposited onto a diluted acrylic paint, it will form fractal fingers. And the reporter's focus is about the geometry and the dynamics. And as for the summary of the report, the phenomenon is the constant diffusing motion formation of fractal fingers. And the theory includes diffusion, which includes gravitational effect, Magnolian effect, and surface tension, and also Pellice's cell and experiments, Navier-Strauss equation, which is Newtonian fluid, and Stefan's-Taylor instability, Darcy's law. And as for the experiments, the factors includes the concentration of acrylic paint, mixture, speed of the droplet, and as for the analysis, the reporter analyzed the maximum length of the fingers, scoring speed, and geometry. And as for the pros and cons, the pros that the reporter experiments to test different parameters, and he has clear demonstration of experiments. And he defined what fractal really means, and he has a comparison between theory and the experiments. And as for the cons, he has some certain graphs with unreadable text sizes, and he missed meaning of labels on certain slides. Okay, so now I want to have a discussion with the reporter. So first, what if the droplet was dropped on an uneven surface, and how can you ensure that the surface is even?
Well, like I have stated in my theory, that's the segmental instability caused by viscosity difference and perturbation.
Yes.
So the perturbation one is like you have stated that uneven surface. So like in my experience, I try to make every time to make the surface become smooth, but there will still have some perturbation maybe caused by the environment or like there is wind blowing it. So the perturbation will cause the droplets to grow fingers.
But what do you think about if the thickness of the surface is uneven, it will affect the dry out time of the base?
Thickness. So I think that if there is a high part and lower part, then there will also be a gravitational effect to make the fingers grow. But I think that because in my experiment I try to make the acrylic paints to become really thick. So I think in my experiment you don't have to consider the depth of the acrylic paints.
Okay, so why do you think in that slide, and on the right side of the right picture, why isn't the diffusion radial?
So can you
Why is it a circle? It's not quite even with the fingers. Yes.
Also because like I have said that the perturbation is unevenly being on the surface. So like maybe some parts there is the rim is not like really go out. So there is less perturbation, which makes the fractal fingers transform. But like you can see the parts here or like maybe here, it is coming more out. So there might maybe some more perturbation, and also that because when we deposit a droplet, the velocity from the everywhere it wouldn't be the same. So it may caused by the velocity difference and also the perturbation difference.
Okay, so do you think that if the surface is even, it will make the fractal fingers form
So do you mean you don't consider perturbation? Or like you just make it to become smooth?
I make it to be young person? And
Because they will still have some they will still have vector fingers, which they will still have perturbation and viscosity difference.
and I have a question. So how do you dilute the
Okay, so I
face?
ate different proportion of water into acrylic paints,
Oh.
and I mixed it.
So do you know that there is a thing called pouring medium?
This
Yeah, so why didn't you use that instead of
you mean the porous?
porous? Pouring medium, sorry, pouring medium. It's
I'm not really sure.
it's okay. And can you turn to page 9? Can you say again?
How?
Yeah.
Okay, so for diffusion, because of the gravitational effect, so the droplets will become flatter, and then it is the Marangoni flow that will start the actual diffusion. Yes, that's the Marangoni flow caused by the evaporation difference, and it makes the droplets grow. And it is when the surface is the same, so it will start diffuse. And for the fractal, I explained with segment pattern instability, which this will caused by perturbation and viscosity.
Oh, and have you tried to examine the fingers with microscope? Because I think in your picture the fingers are bleeding, like it's blurred.
It is blue. So actually, as for the definition of fractal, the finger will keep growing, and you can see that it will become blurry. It is because of the water at the acrylic paint layer. So it will like dilute the fingers.
So you didn't like analyze how well the fingers like separate, divided into 2 branches with fingers, right?
Like the structure.
Yeah, the structure.
I didn't actually measure that because fractal will keep going. Although I say that it was dark when we watch from camera, but a fractal motion will keep going in a scale that with naked eye we can find it. So I didn't actually try to measure the structure.
Okay, so your focus is how the fingers diffuse instead of the actual structure of this. Okay, and can you state again how you compare your the phenomenon with console, your model?
So we can feel that like when we add less water, the figures will be shorter and it's hard to see like in a console when there is no viscosity difference. There will be fractal fingers, and when it increase, it will change the rim. And you can feel that when we add more water into it, the fingers will become more complicated as the in the console.
And can you restate again about the brane state equation? Yeah.
So like which point? Or like the whole equation?
Yeah. The whole.
So the brane rates will be affected by the u0, which means it is the velocity that you drop the droplet. And it will also caused by, you can see u2 minus mu1 and u1 plus mu2, which is that viscosity will also impact the brane rates. And here is the perturbation that we count in the perturbation, so that the brane rates will become slower over time.
And as what I mentioned before, I have mentioned about different kind of alcohol. So what do you think about it?
I think if you change different types of alcohol, maybe it will change the evaporation speed, which may make the Marangoni flow's velocity change.
And how are the properties? Like it will become like oilish, oily, and more viscous, and like oily and yeah.
Yeah, so like if it evaporates faster, which makes the Marangoni flow is faster. So for my guess that maybe the fingers can grow further and become more complicated.
Okay, and can you go to the temperature page? Since you mentioned the evaporate,
Like temperature.
yeah, the slides you mentioned about it. Oh, yeah. So since you mentioned about the evaporation of the alcohol, so have you considered about that the temperature difference might affect the evaporation?
Yes, the temperature may also affect the results. And I think that because in my experiment, I try to control every experiment's temperature to be the same. That's I put the fluids in a temperature maintainer. So that's maybe you wouldn't have a condition that the temperature will change.
And how about the time intervals? Because you mix the mixture, and did you fix the time intervals? Because if the time intervals is longer, the more it will evaporate.
It's fine. I think that maybe at the time, maybe around 50 to 20 seconds, the diffusion would be slower, and it will be the fertile fingers parts. So I don't think that if you try to increase the time, the evaporation wouldn't have a big effect on my experiments.
And then that surface tension is related to temperature. So what do you think about if I change the temperature, and what was the?
If you change the temperature.
Yeah, and what will it affect the surface tension and the?
I think that when the temperature change, and that's because like I've mentioned that the diffusion will be stopped by when I have stem surface tension. So I think that the time of diffusion may change when you change the temperature of the surface tension. That's when maybe when temperature change, the surface tension will change also. So that's I mentioned the Marangoni flow will stop when there is stem surface tension. So maybe it will change the effects of Marangoni flow.
Oh, okay, thank you. And can you change to like page 28?
Yes.
Oh, sorry. Wait. I mean the equation part. Sorry. The equation part.
You mean like the
I want the segment. Yeah. So can you restate it?
Okay, so the growing rates will be affected by initial speed and viscosity, and also consider the perturbation.
Okay, we have to stop here. So have a 1 minute summary of your discussion, please.
Okay, as about our discussion, the reporter has considered a lot of parameters, and he also built a model that fits his theory. However, I think he could discuss more about the temperature, and maybe he could try like different types of alcohol in alcohol mixtures, and also and I think he has a really great definition of like the terms of the fractal fingers and the definition of fractal. Thank you.
Okay. Now let's have questions from the reviewer team.
Okay, so question for both reporter and opponent. Can you list out all the relevant parameters that you think that should be investigated in this phenomenon?
Okay, so in my experiment, I think it will be influenced by the initial speed and viscosity of the two different fluids and also the droplette speed. And also from the opponent, she suggests me that maybe if it will change the temperature, it will also change the surface tension and the viscosity. So that will also change the effects.
And for me, I think it's the concentration for both the diluted paint and the mixture, and also the temperature. And I think that time intervals might also affect the phenomenon.
Okay. And again, question for both participants. How do you think temperature affects the phenomenon?
So the temperature will cause the viscosity change. That's when temperature is higher, the viscosity will be lower. So it may change, like in the equation, the mu1 and mu2's value. So which will also change the flowing rates.
Well, I think maybe the temperature will affect like how fast the alcohol will evaporate. So it might influence the size of the fractal finger.
And finally, question for the reporter. You mentioned that the R value for getting like the complication of the fractal finger, it goes from simple to complex to simple. What do you think the threshold of R value from complex to simple is?
So if this is ideal, so that the structure will become more complicated. But since that in this, the water will dilute the structure when you add more water in acrylic paint. So I think it is because of the dilute of the water that makes the structure go back to simple.
Okay. And also, when you measure finger lengths, did you take an average, or did you take an average of all the finger lengths, or the certain fingers?
I try to measure like the four direction, like up and down, left and right, and I do the average.
Okay.
Okay, so prepare for the presentation. Time is up. You begin with your presentation.
So my name is Peter, I'm from United, and I'm the reviewer for fractal figures. Next slide. So again, like problem statement as stated by both reporter and opponent, is the effect of fractal figuring. And then the main focuses, we think that the main focuses are the geometry of the fractal figures and the dynamics of the fractal figure. So for the reporter, so we think that the reporter, pros of the reporter are clear visual phenomena and then mechanisms to make sure that the starting parameters are consistent, and then cons are unclear gas, and then test some parameters such as alcohol, other types of alcohol and temperature, and the phenomenon he describes the diffusion and formation of fractals, and he uses surface tension and gravitational forces to illustrate. So the opponent questioned the reporter on the even surface effects on figures and also the types of alcohol's effects. And they also, I think they brought up relevant concerns such as uneven surface and cons and negative effects. So first they discussed the effects of alcohol. So the opponent suggested that they test different types of alcohol. And the reporter only used alcohol, but stated that alcohol may have an effect on the evaporation speed. And we agree that different types of alcohol with different viscosity and certain tensions will have an effect on the phenomenon. Okay, next, the opponent inquired on how temperature would affect the phenomenon, and the reporter stated that he kept the temperature consistent and the surface and like if temperature is changed, that will affect the surface tension, and therefore the variable will flow. And then we agree that temperature would affect the gravity speed, and to a lesser extent the surface tension it should be considered as a parameter. And next was the uneven surface. They asked how uneven surface will affect the fractal figuring. So the reporter stated this is account for perturbation, and we agree that uneven surface may cause like a skew in the fractal figuring, but it shouldn't have too much effect. And photo talked about the structure of the fractals, and then the reporter mainly focused on diffusion and not structure, and we think that the structure should also be analyzed. And then opponent talked about using a microscope to take a deeper look, and then the reporter stated that the fractals grow and like they move the fingers, and we think that the microscope should be used for data clarity. And explanation. And then next, opponent inquired about the equations describing console simulation, and then the reporter also showcased clear governing console equations. And then the opponent asked about how the time of intervals may affect, and then the reporter stated that there won't be a big effect besides the evaporation rate, and then we agree that it won't really be affected too much. And we think that coincidences are like attack compensation of quantity of figure out stress. There's randomness in the fractals which we think were not explored, and then there's quantitative explanation wasn't really sufficient.
So concluding remark from the reporter.
Okay, so first I'm going to talk about my fixing part. That's from the opponent's view that I can try to discuss about different alcohol, like ethanol or methanol, which may affect my result. And second is that I can try to conduct experiment under different temperatures. But since that, because I think other parameters like the concentration of occludipants and the in alcohol mixture or the initial speed, I think that maybe the opponent can focus on my parameters and try to discuss about the data. And the third is that the opponent says that when increase the timetable, it may make the structure or length of the fingers will get bigger. But from my experiment, because I'm just trying to focus on the growing speed, so I'm just trying to focus on the growing speed at first. And so for the discussion revisit that I had with component, components. That's first we talk about the uneven surface, which I explained that there will have some different perturbation. And the second is that we talk about the temperature that maybe will affect the surface tension and viscosity, and which I think that maybe it can be the future one. And the third is that I restate the phase about diffusion and fractal motion. That's the diffusion will caused by surface tension and the gravitational effects, and fractal caused by sedimentary instability, which will caused by the viscosity difference and the perturbation. So this is my concluding remarks. Thank you.
Okay. Let's take question from the QB members. Yes.
Opponent. You asked many questions. So do you agree his argument? The reporter's argument. You asked many questions, actually. So I just want to know, do you agree his argument? Yes or no?
Yes.
Yes? Okay, then would you tell us why or how fractal fingers appear?
Why do fractal fingers? Well, I think it's just like what the reporter said. It's first it's because of the magnetic effect. It will make it diffuse. And as for the branches, I might thought about some energy. Like as the velocity decrease, the energy, so decrease animal stuff.
Yeah, thank you. How about you? Do you agree with this argument?
I guess, yeah.
Okay, then why don't you tell us how or why the fractal fingers appear?
So Colin just said, the paint diffuses and due to okay, so and then when the surface tension decreases, it diffuses and then decreases surface tension, and then when the surface tension decreases to a threshold, the fingers will appear.
So give us a very simple explanation why it appears.
Okay, so like a simple explanation will be considering the viscosity difference in the perturbation, and also
Why? Why?
because
You're talking about so many factors, but why it appears?
and so
Simple explanation.
So I think like where there is a perturbation, so when the droplets reach there, it will grow like a fractal-like structure.
Yes.
May I see about you compare theory, simulation, and experiment picture? Did you think your simulation and your experiment is matched?
Yes, I understand. Like when individuals are talking about the like this picture, it wouldn't have like fractal fingers to be
Have some
even.
different? Why?
And it is because that in terms of it will simulate that the upper fluids can like infinite giving into the downward fluid. So that's maybe in my experiment, if I try to like with time increase the amount of the mixture, it can also have the structure like this one.
Thank you.
Any other question? I just have a simple question. What is this K? The variable K. What does this stand for?
Okay, so the K stands for wave number, and
Uh-huh.
U0 stands for the initial speed that I drop my mixture. And the mu2 and mu1 is the lower one, that's mu1 is the upper mixture viscosity, and mu2 is the down equivalence viscosity. And so here is the perturbation, that's the gamma represents the surface tension.
So this is some kind of instability, right?
Yes,
Yeah, and it depends on how large K is. Is there a critical K?
I think there might be a critical case, but I didn't measure that.
Okay. All right. So let's move on to the grading. Now let's show the grade. Seven, 9, 7, and 9. And then for the opponent, 5, 5, 6, 6, and 7. Finally, for the reviewer, 6, 5, 7, 7, and 7. Okay. I would like to congratulate all the 3 teams. You have made it through the most difficult parts, the first physics fight. I believe that it was going